Hello and welcome to Lecture 3. We're going to be looking at velocity, and in particular velocity as a rate of change. Velocity is a rate of change of position. Let's just understand rates of change with something more familiar. Suppose you work 80 hours and you make $800. Then we can talk about the rate of change of your money in the bank, your pay rate. And it's going to be the change in bank balance over the time, where I'm just going to talk about hours worked. And so that's $10 an hour. Simple enough. A velocity really works in exactly the same way. We're talking about the rate at which the position changes, and so it's going to be a change in position, a displacement, over a time interval. Technically, that definition is an average rate of change. To understand that, let's take another look at your bank balance. So you make your $800 for the 80 hours worked. But it's not that you work 1 hour and you find yourself $10 richer, and after 2 hours you've made $20 and so on. You would see no change in your bank balance for most of the week. And then suddenly on payday, bang, you get your $800. But the net effect over those 80 hours is the same as if you had made a steady $10 each time you worked an hour. So this is the idea of an average rate of change. When you have a varying rate of change, the average rate is the constant rate that would have the same net effect. Now, of course, in the real world, these 80 hours that you're being paid for are probably for the previous 2 weeks and so on. I'm ignoring things like that because this is a physics course, not an accounting course. And unlike accountants, physicists like to keep things simple. So let's take that idea of an average rate of change and apply it to velocity. So an average velocity is a displacement over the time interval that it takes place in. And so think about that. The net effect in our putting example was that in 8 seconds, the ball ends up 7 meters up the hill from where it started. And so an average velocity, which is going to have to do with what the constant velocity would have to be to have the same effect, is going to be just from that net displacement over the time it took. Whereas the average speed is going to be the same idea. The total distance traveled, okay, so here's our total distance traveled. That's the net effect of this motion over the time interval. And so that's going to be 9 meters over 8, seconds. And just realize the velocity wasn't constant. It was going uphill and fast here, uphill and slower, uphill and slower, uphill and slow. It stops, it goes downhill a little faster, then slows down, right? So the velocity would have been changing this whole time, but we can still talk about an average velocity, which is the constant velocity which would have had the same net effect. Let's look at how this all plays out in a graph. So here's a table of values for x versus t, and here's a motion diagram, and we're going to draw an x versus t graph. Now, if you're used to your vertical axis always being y and your horizontal axis always being x, this might bug you to have x vertical and t horizontal. But that's what we've got. We're thinking of how x varies with t, right? And so we're going to do an x versus t graph, x versus t, right? And hopefully you know that if you are graphing a versus b, that means a goes, whatever it is, goes on the vertical axis. So I will not use the terms x-axis, y-axis. I will say horizontal and vertical, unless they really are x and y. So in this case, I have a t-axis and an x-axis. So I'm going to take this motion diagram and I'm going to turn it into an x versus t graph. And you should pause the video and do the same thing and check that you get the same graph as me. Okay, so there's my graph all drawn. And one thing to notice is that I haven't connected the points. Now let me just talk about why you would or wouldn't. If you really believe that x is lying on this line connecting these points in between the points, you would draw it. And I think we can agree it seems likely that it is. It looks like this thing is going along consistently. Now notice how the slope changes in this next part. Okay, so exactly what happens there we're not quite sure. I'm going to come back to this part. I'm going to finish. Notice there's another change in slope there. And there. And now here, we don't really know what happens. Maybe it goes past here, stops, turns around, and passes back through, or maybe it really stops. So the graph could look like this if it goes past this point. But for sake of argument, I'm going to say that we know that it actually stops. And there are some unphysical things about this, but we'll talk about that later. Now, we can find some velocities here because we know a velocity is a displacement over time. It's a rate of change of position. And so if we write that, v, and I'll say this is an average velocity, this is an average rate of change, is a displacement over a time. So look at how that plays out. If we wanted to know v av from 3 to 6, we're using this delta x, and we're using this delta t, right? So that's going to be 11 meters minus 2 meters over, that's a 3-second time interval, right? It's 6 seconds minus 3 seconds, and that's going to come out to 3 meters per second. Now notice something. On the graph, that's a rise over run. So a velocity is a slope, specifically a slope of the x versus t graph. That's very important. I'm going to pause and get the velocity here. Okay, there's the velocity here. Notice it's changed sign, right? This is now going back to the left. And we've already defined right as positive. And so the sign convention for positions carries through for velocities. Now, I just want to caution you about something here. There's a difference between these velocities, which are averages, versus if I were to say, what is the velocity at 5 seconds? Okay? Well, normally if you had a curve, you would take a tangent line to the curve, but this is a straight line. And so the slope is the same everywhere here. And so we know, because the velocity is constant through that whole time interval, that v at 5 seconds is the same as this average velocity. It's 3 meters per second. But now I want to draw your attention to a mistake that many students make. You've probably seen this horrible thing. It's wrong, right? You might have seen it as d over t. Wrong, wrong, wrong. Forget it. Let me show you why it's so dangerous. If you take it seriously, and frequently students do, you would say, oh, well, the v at 5 seconds. Well, at 5 seconds, x is 8 meters. 8 meters. And t is 5 seconds. And so that gives us 1.6 meters per second. Now notice that's nothing like the 3 meters per second here. What's happened is, if you think of this as a slope, it's like saying, oh, this thing went 8 meters in 5 seconds, and so it followed this line. But you can see from the x versus t graph, it did no such thing. And so this velocity, or this attempt at a velocity, is calculating a slope of a line that doesn't even exist. Okay, to finish up what we're doing with this, I'm just going to take my x versus t graph and I'm going to turn it into a v versus t graph. So I've just compressed this a little vertically so I could fit this in underneath. The first thing I'm going to do is I'm going to note where there are changes. Look, the slope of the x versus t changes here and here and here. Notice I've lined the v versus t graph up directly under my x versus t graph to make this easier on myself. So now that I've identified where the changes take place, I can draw in the v versus t, and I know that this is a slope of 2 meters per second, and you can check that if you wish, and that's a 3 meter per second slope, and that's a 0 slope, and that's a negative 2, and that's a negative 3 meters per second. And there we go, there's our v versus t graph. Okay, we've done quite a lot, so it's time to summarize a few things. We've seen that we work with coordinates which need an origin, which is where the axes cross, all the coordinates are 0. Any change is defined as a final value of the thing minus the initial value. Position is a location that we've assigned numbers to, and it has direction information associated with it. A displacement is also directional. It's a change in a position, and it's quite different from a distance traveled. And a velocity you can think of as a speed with direction. It's a slope of x versus t, in other words, a displacement over a time interval. And speed, on the other hand, is a distance traveled over time taken, and we've seen that that is usually different.